We shall now classify the divergences for lambda n by factorial n pi to the power n. So small n is fixed. So what we can do is to write the superficial degree of divergence omega entirely in terms of the number of external lines and the vertices. E and B. How do you do that? Use the two identities. One is n minus L equals n minus B plus 1, which we had derived earlier. It's a property of the graph that we had derived earlier. Another is n times V must be equal to E plus 2n, because this n times V is the total number of lines emanating from all vertices. If there are V number of vertices and each vertex has n lines coming out, then the total number of lines that are being produced by those vertices is n times V. And all such lines add up to produce all these internal and external lines. However, each internal line is counted twice in this process. As it's connected to two vertices always, right? So each internal line will be connected to two vertices. So in this process of counting the total number of lines, you're counting internal lines twice. This explains the factor of 2 on the RHS. Now, notice one thing, that using these two relations, we can eliminate V. You just set V equals E plus twice capital N divided by small n and substitute that here. Then you will get a function of L, N, and E equal to 0. Which means that if you fix, let me write F, E, L, and N equal to 0. Right? After eliminating V, you will get such an equation. That means that if you fix E and L, N is fixed. And that is the reason why that gamma tilde E where had this I, where we had L comma N. And I mentioned earlier that for a fixed value of E, when you choose this L, then when you fix L, then N, the number of internal lines, is also fixed, and that's a result of coming from using these two equations. That was the reason for this notation. This is a result coming from these two equations, and this is true when we fix small n. If we mix up various values of n, then it's a slightly more complicated reasoning. So now using these two equations, we can write L now for the. So this is just to explain that notation I, L, comma n. And now let's come back to this superficial degree of divergence and discussion of that. This is L equals half n times v minus e minus v plus 1. That's how you can write using these two equations. So so we basically eliminate a number of internal lines. Instead of eliminating v, we are eliminating number of internal lines n, and expressing L in terms of v and e. And if you substitute that in the expression for omega, then omega with some amount of massaging, you can write this. So omega will be d half nv minus e minus v plus 1 minus nv plus e. And that can be written as d minus half d minus 2 times e minus delta times b, where delta is n minus 2 by 2 d. And this is nothing but the mass dimension of coupling lambda n. We can call it delta n also. Yeah. Now let us discuss what a mass dimension is. Let me explain that a little. Maybe I need some more space here. Anyway, so this is an aside. Calculating mass dimension. So we are working with in a unit c equal to 1, h bar equals 1. The dimension of c is L by t, and that being 1 implies that L and t are same, which means that we are looking at both spatial length and temporal length to be as a unified length. We are not distinguishing them. So both L and t are same, and the dimension of h bar is angular momentum. Angular momentum is r cross p, so L times m times velocity, L by t, but L by t is 1, so it is L times m, and that h bar being 1 implies that m is same as 1 over L. So that means all the four dimension length dimension are same. We are not distinguishing between space and time. That particularly suits the relativistic discussion. And we are taking h bar equal to 1 unit means that we are identifying mass to be as in length inverse, length as mass inverse, and vice versa. Okay, so that means you can calculate dimensions of anything in terms of only length dimension or mass dimension. So that is very useful here in the context of quantum field theory. So action, the dimension of action should be 1 because it's h bar, and this action is given by integral d dx times the Lagrangian density, and this Lagrangian density, because of this fact, since this entire thing should be 1, dimension 1, and this has length dimension d. So this must have length dimension minus d. Length dimension minus d means mass dimension d. So this Lagrangian has m to the power d. So that is the mass dimension, m to the power d. Now Lagrangian has a term, kinetic term, which is del mu phi, and del mu is a derivative. This derivative is dimension of the derivative is 1 over L, length inverse. So this is L to the power minus 2 because of the two derivatives, and so the dimension of phi square will be, so let's calculate the dimension. So 1 over L square times dimension of phi square must be m to the power d. That's a term in the Lagrangian, and Lagrangian has is m to the power d, and this implies the dimension of phi is equal to m to the power d minus 2 by 2. So this L square goes this here, so it becomes L square here, so that is d minus 2 and divided by 2. Similarly, the Lagrangian also has the potential term v, which is lambda n by factorial n times phi to the power n. Now lambda n is a coupling parameter, and that also can have a mass dimension. And to calculate the mass dimension of lambda n in this sense is to require that v is equal to the mass dimension of lambda n times phi dimension to the power n, and dimension of phi is m to the power d minus 2 divided by, so n times d minus 2 divided by 2 times lambda n should be equal to m to the power d, because it's a term in the Lagrangian. So this gives you the dimension of lambda n to be equal to m to the power d minus n by 2 times d minus 2, and this is what we call delta n, and delta n you can also write in this form, n minus 2 by 2 times d. That's the mass dimension. Okay. So omega, let me recall, my d minus half d minus 2 times e minus delta n times v. So this is independent of v, number of vertices, when delta n is equal to 0 for dimensionless coupling, if the coupling is dimensionless. So delta n equal to 0 when n is equal to 2d by d minus 2. That you can get by solving this equation. Set this equal to 0, n equal to this. So that means phi 4 in phi to the power 4 in d equals 4. So in 4 dimension, phi to the power 4 interaction is dimensionless. The coupling is dimensionless because if you say d equals 4, then it's 8 by 2, that is 4. So n has to be 4. So in d equal to 4, phi to the power 4 interaction coupling is dimensionless. So if delta n less than 0 would mean n greater than 2d by d minus 2. Now these analyses, all these expressions are not valid for d equal to 2. For d equal to 2, if you have d equal to 2, then here, so you have length square here from the measure and 1 over length square from the two derivatives, and therefore phi is dimensionless. So phi is m to the power 0 or 1, which means that delta n equal to 2 for any n greater than or equal to 3. So delta n equal to 2 because it has to cancel the L square. So that should have mass dimension. So phi is dimensionless. It doesn't matter what is n here, 3, 4, 5 doesn't matter. It doesn't contribute to the dimension. And the lambda n should have mass dimension 2 to cancel the L square coming from the measure. So that's why we have delta n equal to 2 for all values of n. Now there are certain scenarios. There are 3 scenarios here. One is that n less than 2d by d minus 2 in general, for general dimension. Then delta n greater than 0 which means that more vertices means more superficial convergence, because delta n is positive, and in the superficial degree of divergence it comes with a minus sign. So more vertices implies more superficial convergence. If n is same as 2d by d minus 2, and in that case it is the coupling is dimensionless, and then superficial convergence will happen beyond the threshold value of E, irrespective the number of vertices. What it means is that if this term is absent, so the number of so V does not affect superficial degree of divergence. Since E is coming with a negative sign here, provided D is greater than 2, E is coming with a negative sign. So this will be for a threshold beyond the threshold value of E, it will be convergent. It will be negative. So therefore, superficially convergent. So this means when for a dimensionless coupling, you will have superficial convergence beyond a threshold E, irrespective of V. Then for n greater than 2d by d minus 2, delta n is less than 0, and that means more vertices implies more superficial divergence. Because delta n is negative, at the same time it is coming with a negative sign in the superficial degree of divergence. So this is growing with the number of vertices. More vertices means more superficial divergent. So all this, so this is the classification. Next thing to understand is that we have done the classification in terms of superficial degree of divergence, but we keep using this word superficial. What does it actually mean? Is it not real? So our next job is to see what is not really real in this superficial counting of divergence. We have to clarify that. So that we'll do in the next lecture.